Day 3. We're still working on our objective. Our objectives, several of them about parabolas. You know, how do you make this happen? So understand the geometry of parabolas and their key features. Well, I'm looking at this and thinking, how am I supposed to know that's a parabola up there? Prove that the graph of y squared minus 6x plus 2y plus 13 equals 0 is a parabola, and find its vertex, focus, and directrix. Well, if I could get it to look like this, or this, that would prove that it's a parabola, and I could get the graph. So, what does something like that have that other equations, second-degree equations, wouldn't have? Well, it has either an x squared or a y squared, but it doesn't have both. Got a y squared, no x squared either. So I should be trying to get it to look like that. Now, how to make that happen? There's a binomial that needs to be squared. So I need to figure out how to make stuff that doesn't look like something squared into something that does look like something squared. Excellent. So here's what we're going to do. So we're going to make sure all of our stuff with y is on one side of the equals. We're going to move everything off to the other side because we need to complete the square. So we will have y squared. I don't need that 6x over here. That doesn't have anything to do with y, so I'll move that over to the other side. I need the 2y, but I don't need the 13 over here. That'll move over to the other side. Next one. Now, if there were a number in front of a y squared, we'd have to factor that out first in order to make sure that this is going to work. But we've just got y squared plus 2y, so and I'm just rewriting it again so if somebody's gone, you can see what we did. We want to fill in this blank with that c value that will make that a perfect square binomial. And whatever we do, we have to do the other side as well. And this all comes back to that really little formula. B over 2 squared. That's what we do. Where it's ax squared plus bx plus c, we're going to take b, which is 2, divide it by 2, and square it. Well, that's 1 squared. And that's 1. But whatever we do to one side, we have to do the other. So now, that is a perfect square trinomial.
I just saw that
Steps, so we can see the completing the square. Just go through the steps of completing the square so we can see those steps. It's like an algorithm. We have to see that you follow the steps of the algorithm. All right, this would now be y plus 1, the quantity squared, and this would now be 6x minus 12. Now, the left-hand side looks great. That's bad. But I need to figure out how to factor something out in order to make that look like 4p times x minus h exactly. That's my proof. It's an algebraic proof. But what we did was we started with a second-degree equation because it has that y squared piece up there, and worked ourselves into that parabolic equation that we like to see. So now we have to figure out vertex, focus, directrix, all that good stuff so that we can graph this. So be careful because this is the first one we've done today. What's the vertex? 2, -1. Yep, look for your x and then your y. All right, so 2, -1 vertex. Which is this little one? Right? Let's see. So it's going to open to the right. That means it's going to wrap around my focus to the right. But how do I figure out where that focus is? A little 4p has to be 6. So p is going to equal 3 halves or 1 1/2. It has to go to the right. 1 1/2 this way to my focus. And I realize that would be adding to the x. So I've got 2 plus 1 1/2. And that would give me 3 1/2, but we probably better make it an improper fraction. So 3 1/2 would be the proper fraction. There's our focus. Directrix. Where's that thing go? Equal but opposite. So okay, now we're going to go back 1 1/2. There. So what's the equation for our little directrix? Okay. Proof that it's a parabola, did that. Vertex, focus, and directrix, did all that. We wouldn't have to, but I really want to graph that. It's driving me nuts to have everything up there. So what's the quick and easy way you can graph this? So 6 divided by 2 would give us 3. So 3 up and down from the focus. And as I've said before, if this is a test, I'm probably going to put in another number out here somewhere just to make sure I have everything exactly as it needs to be. But boy, having that book really helps me. It's really nice, quick, and easy graph. Now look at all that blah, blah, blah. That looks kind of scary. Wow. This is explaining that a lot of things that we see in life are parabolic and why they're parabolic. So the main applications of parabolas involve their use as reflections of sound, light, radio waves, and other electromagnetic waves. You think about spy shows, and it truly is something they do. They use little dishes that are hypersensitive to sound, and they'll point them at a building, and it focuses in the sound so they can hear what people are saying inside a closed building. And that's something they actually do. Now, if we rotate a parabola in 3 dimensions, in 3-dimensional space about its axis, the parabola will sweep out a paraboloid of revolution. If we place a signal source at the focus of a reflective paraboloid, the signal reflects off the surface in lines that are parallel to the axis of symmetry. This property is used in flashlights, headlights, searchlights, microwave relays, and satellite uplinks. So here's how it works. Either the light from the focus shines up and hits the side of the parabola and then shoots out in that parallel pattern. And that's when you want something to leave the parabola. But when you're receiving information, you have these incoming signals that hit the parabola and then all bounce together right at the focus. That's what the focus is for. So that's how it collects all of that sound up or makes a really bright light, is by using that parabolic surface to bounce off, reflect on. The principle works for signals traveling in the reverse direction as well. That's what we saw in the other one over there. Signals are still arriving parallel to the parabolic reflector's axis, and they're directed towards the focus. So the gist of this is the focus is important. That's why it's called the focus. That's where you want things to end up, is at that spot, or begin is at that spot. So this property is used to intensify signals picked up by radio telescopes and television satellite dishes, to focus arriving light in reflecting telescopes to concentrate heat in solar ovens, and to magnify sound for sideline microphones at football games. To hear aliens and stuff. That one. You'll see in all the spots where they're out there listening, to these huge parabolic dishes, trying to grab in any of those sounds and make sense of them. they're using the parabolic shapes. So, all that scariness for a problem that's going to take us all of maybe 3-4 minutes. You know, it's just one of those things. So on the sidelines of each of its televised football games, the FPTV network uses a parabolic reflector with a microphone at the reflector's focus to capture the conversations among players on the field. Some of those are conversations you really don't want to hear. If the parabolic reflector is 3 feet across and 1 foot deep, where should the microphone be placed? Now there's a picture over here, and that's to help us out. Because what we want to do is place this in the most basic, easiest place possible. And that easiest place is to have your vertex at 0, 0. So if they didn't give us this picture, it wouldn't make much difference. We would want that parabola to have its vertex right there at 0, 0. That's what we would want. And then we try to figure out the rest of the numbers and how this would work. It says if it's 3 feet across, okay? There to there, 3 feet. It doesn't take us long if we've set it up at 0, 0 to figure out, well, if I split that in 2, I'll have 1.5 here and 1.5 here, which means the x coordinate to this point is 1.5. And then it says it's 1 foot deep. Well, we've got it drawn. This is the 1 foot right here. And here. So you get to choose whether or not you want to work with positives or negatives. I think most people are going to choose positives. Rather than try to keep track of the negatives. So where should the microphone be placed? At the focus. That's where we want it to be placed. But we don't know the coordinates of the focus. So I think, okay. It opens up. And we made sure that our center is at 0, 0, so we don't have to use the big long formula. We could. I need P. If I can find something to put in for X and Y, I can find it. Oh. 1.5, 1. There's X and there's Y. So X is 1.5. That's 1. Well, if I want P, all I'm going to have to do is take 1.5 squared and divide it by 4. That's what that is. 1.5 squared divided by 4. 0.5625. Well, you know, as far as decimals go, it's not beautiful, but maybe there's something we can do with that. Let's see. The parabolic reflector was 3 feet across and 1 foot deep. Oh, so this is feet. So, since we don't have to write a formula for it, we just want to tell them where it's going to go, this might look a little nicer in inches. It might. So let's go ahead and take our 0.5625 times 12. And see if it's a little bit nicer in inches. That's a little better. Now we can't just say 6.75 inches. So there's 2 ways we could do this. We could reference our picture and say, okay, it's going to go at 0, 6.75. But what if, just throw something out there, what if you started yours by drawing this as opening to the right instead of opening up? Did this say that this microphone was going to be pointed up anywhere in the bottom? So maybe you used y squared equals 4px. Turns out it doesn't matter. Either one of them will give us the same like that. But what we want to do is let them know, okay, generically, if you didn't use up and you use sideways, how do you tell somebody where this goes? Well, it needs to go 6.75 inches from the vertex through the focus. That's what we tell them. And and that is the axis of symmetry of this parabola. So 6.75 inches from the vertex along the axis of symmetry. And there'll be no mistake. Whether or not they had it open up or they had it open to the right won't make any difference. They'll know exactly where that focus is to go in order for this to work. Well, that seems way too easy after 2 paragraphs full of blah, 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 doesn't it? That was it. That was it. Use the information you have and find out. So, 43210, how you feeling about the little application problem we had here? Yeah, it's still a word problem, I know. I see more for you on the word problem stuff. But I know you can do these. I know you can. Remember, they're not as difficult as they look. So if you see a lot of blah, 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 don't let it scare you off. We're going to set up our parabolas with a vertex at 0, 0. Make our life nice and easy. Put an X and a Y in. That'll help us find P. This is another one that went really fast, by the way. It's nice and short. And work time, what a banner day! Got the test done. Let's do the problems. And that's work.
How does that?
Yeah, let me get the. Let's go. Oh, what's up, Nate?
I'm gonna be gone Thursday and Friday for class. So I thought you signed this. They ran out of sheets, so I just choose one of those.
Are you going to be responsible and watch videos and
Yes.
do work?
For sure.
Yep. Date it or something so it looks official.
Do you have any more Kleenex?
Yeah, there's another box, like the next shelf up. Should be flat against the cabinet. We'll try to keep a spare. All right, so get our vertices, and we have to round them. 0, 35, 20, 0, 9, 13. Put it into the objective function. This. Oh, it maybe looks like 9/11. Does it do a little off with the graphing? It looks like 9/11, but if you use the graphing calculator. Oh, no, but it should. All 3 of us went through it. Yes, thank you.